In this video, I'm going to talk about crystal field splitting, in which the ligands in a coordination complex change the energies of the d orbitals on the transition metal so that they don't all have the same energy anymore. And the reason why that's relevant is that we observe color when specific wavelengths of light are emitted by a sample, as we saw with the Bohr line spectra, or when specific wavelengths of light are absorbed by a sample, removing them from the colors reflected by the sample. And so therefore, we would wind up observing the color that is the combination of the reflected colors and not the color that was absorbed. Both of those processes require there to be an energy gap corresponding to wavelengths of visible light. So in order for us to understand what's going on here, we have to remind ourselves of what our coordination complex looks like. And there's a schematic on the left here with this dot in the middle representing our transition metal cation. And here we're looking at an octahedral complex. All of our discussions are going to involve octahedral complexes to keep things simple. And so in an octahedral complex, we have 6 ligands, 1 above, 1 below, and then 4 around the middle, 1 pointing along each axis in each direction. You will remember that we have 5 d orbitals in the d subshell on that transition metal cation, and they have been drawn in front of you. We have the dxy, the dyz, the dxz, and then also the dx squared minus y squared and the dz squared. Now, if you look at those pictures in front of you, you can see that 2 of those d orbitals are pointing straight at the ligands. And so our x squared minus y squared is pointing right along these axes, right at the ligand. And our dz squared is pointing up and down with the donut around the middle. My picture's getting really messy and cluttered. But what you can see is that those 2 orbitals are pointing directly at the ligands. The other 3 d orbitals are not pointing directly at the ligands. They are pointing into the spaces between the ligands. So why does that matter? Well, think about what our ligands are doing. Our ligands are serving as Lewis bases. They are donating electron pairs in toward the transition metal. And so there is an electron pair forming a bond between the ligand and the transition metal cation. If there is an electron in the d orbital pointing at the ligand, that's a different electron. And electrons are negatively charged. They repel each other. And so the electrons from the ligand that are being used to make this bond here, those will repel the electrons in the d orbitals, and they will repel the electrons in the d orbitals pointing right at the ligands by more than they will repel the other electrons in the other d orbitals. And this then would make it more favorable or lower energy to have the electrons be in the d orbitals that are pointing between the ligands rather than the ones that are pointing right at the ligands. And that sets up 2 different energy levels for our d electrons. And so if we have no ligands, then all 5 d orbitals are equivalent to each other. 1, 2, 3, 4, 5. But if we bring in ligands, and we're again going to talk about symmetrical octahedral complexes for simplicity, the orbitals that point between the ligands are going to experience some repulsion, but not as much as the electrons in orbitals pointing right at the ligands. So we have up here the d orbitals that were pointing right at the ligands, And we have down here the d orbitals that we're pointing between the ligands. And this is referred to as crystal field splitting. That's the name for this effect. And the energy gap between those two sets of d orbitals is referred to as the crystal field splitting energy. And we use this delta symbol with a subscript O for octahedral, which, like I said, all our examples are going to be octahedral. Now, the size of that energy gap is going to be dependent on how tightly the ligands are pulled into the transition metal. And so there's something called the spectrochemical series, which will appear on your data sheet on your final exam, which lists which ligands have the strongest effect on that energy gap versus which ligands create much smaller energy gaps. And so ligands that create very large energy gaps because they are pulled in tightly and make very strong bonds to the transition metal cation are referred to as strong field. And ligands which don't come in as closely and where therefore the difference between d orbitals pointing right at the ligand versus just pointing into spaces near the ligand is not so significant are referred to as weak field ligands. And if we look at the species on either end, it's maybe not such a great shock that a ligand that has a negative charge on carbon, which is a very small atom, would be pulled right in very close to that transition metal cation, making a very short, strong bond. Whereas your iodide ion, which is one of the larger atoms, even though it is an anion, there is a relatively low charge density, and the iodine atom is inherently big, so that's going to be an inherently long bond to the transition metal cation. That's going to result in a much smaller energy gap between d orbitals pointing right at it versus d orbitals pointing between ligands. And so the effect is progressive. If we have no ligands, then all 5 d orbitals are going to be of equal energy, and electrons in any of the 5 would be of equal energy, so there would be no favoring of one over the other. If we have a weak field ligand, then what's going to happen is that all of the d electrons are going to be a little bit repelled by the electrons from the ligands, but those in the d orbitals pointing right at the ligands will be repelled more and have their energies pushed higher. But since it's a relatively weak effect, we have a small energy gap. As we work our way across the spectrochemical series towards the strong field ligands, we see that the energy of the electrons in the d orbitals is continuing to climb. The ligand is being pulled in tighter and it is repelling all of the d electrons more, but the impact on the electrons in the d orbitals pointing right at the ligand becomes significantly more compared to the d orbitals pointing into the spaces between the ligands, and we therefore wind up with a large energy gap. Now, if we were to only have 3 d electrons in our complex, then it would be very easy to decide where those 3 electrons were going, regardless of whether we were dealing with the weak field ligand or the strong field ligand. But where does the 4th electron go? In the no ligand picture, that's a very easy question to answer. We put it in the 4th d orbital. But now the 4th d orbital isn't of the same energy as the first 3. And so then we have a trade-off between, is it better to keep lining up our spins, or is it better to continue filling the lower energy orbital? And the answer to that question depends on the size of that energy gap. If we have a very small energy gap, then it is better for us to continue lining up our spins. And in that case, we get what we would call a high spin distribution of electrons. On the other hand, if we have a large energy gap here, then the energy savings due to continuing to line up the spin are dwarfed by the fact that we would have to throw the fourth electron into a substantially higher energy orbital. And so we don't do that. What we do instead is we put our electron into the lower energy set of d orbitals, and that generates what we would refer to as a low spin complex. And we can reasonably predict that if we were dealing with one of the weakest field ligands on our spectrochemical series, that we can expect high spin. And if we're dealing with one of the strongest field ligands in our spectrochemical series, that we're dealing with low spin. And if you're dealing with something in the middle, we're going to have to give you more information than that. We're either going to have to tell you whether you're looking at high spin or low spin, ask you to draw both of them and talk about them for us, or say, here are two complexes, one's high spin and one's low spin, which is which? And then you can look at the spectrochemical series to see which of the two ligands is stronger field. So how does any of this have anything to do with color? Well, what we have done here by creating those two energy levels, if we have set up a situation in which it is possible for an electron to be excited from one of the lower energy d orbitals into one of the higher energy d orbitals. And so if that were to happen, if we were to excite this electron down here up into one of those higher energy d orbitals, then it would have to absorb light. And it would have to absorb light with a frequency and therefore a wavelength corresponding to that energy gap. And of course, that can happen whether we're dealing with a high spin or a low spin complex. And so it would also be possible for an electron in the low spin complex to be excited from one of the low energy d orbitals up into the higher energy d orbitals. And again, the energy gap there would therefore have to be equal to the energy of the photon that was absorbed. And from there, we can calculate frequency and wavelength. And so the reason that these complexes are colored is because the electrons can be excited from one of the lower energy orbitals into one of the higher energy orbitals. That means we need two fundamental things. We need at least one electron in one of those lower energy d orbitals, and we need at least one empty space in the higher energy d orbital. And so at this point in class, I would be setting up the projector and showing you a video that I remember fondly from my childhood. It's very, very, very old, but it does a beautiful job of illustrating why the absorption of one color makes us see a different color. If you're taking physics, I actually highly recommend the whole series because it works through every concept you're going to see in an introductory physics class at a level that I understood when I was 8, watching it as a cute little cartoon on PBS or TV Ontario, I think it actually might have been. And so I'm going to stop this video here. I'd like you to watch the video linked here. And if you're enrolled in this class, it's the next video down the list on Moodle.